So yeah, today's session is on confirmatory factor analysis, and in some senses it's an introduction to structural equation modelling. The major emphasis is on using Amos to fit confirmatory factor analytic models. So I'm going to give an overview of structural equation modelling, of which confirmatory factor analysis is kind of a subcategory of that, in a sense. Talk about some prerequisite knowledge, and talk about how path diagrams work in Amos with some examples. So why might we do this thing called structural equation modelling? To start with, in psychology, we're often interested in latent variables. And is it clear what a latent variable is? Latent means it's there, but you're not exactly observing it directly. So intelligence is latent because we observed behavior that looks like intelligent behavior, and presumably intelligent behavior is kind of co-occurring across behaviors, and we infer the existence of intelligence by seeing people that, consistently exhibit intelligent behavior. Or if we're talking about it in a very concrete measurement way, we infer extroversion through how much people talk, how much they seem active and lively, how much they kind of seem positive and upbeat, perhaps. Or in a research setting, we might just simply ask people or ask observers to rate someone or rate themselves on a bunch of items, and from the consistency of those items, we infer a latent thing. We infer a latent variable. So most psychological constructs are latent in that sense. Job satisfaction is latent, intelligence is latent, personality is latent. So structural equation modelling provides a way of estimating the relationship between latent variables, rather than using what we call observed variables. So observed variables are the items to a personality test, the items of an intelligence test, the individual ratings of behaviour. And observed variables are also often, just more commonly in psychology, just simple sums of scores or means. So, proportion correct on a test is just a sum or a mean of the items that are correct, and that's an observed score. Likewise with personality tests, you typically just add up the items on a 1 to 5 scale, divide by 5, and that's your extroversion. So that's an observed score. The idea is in psychology, observed variables are measured with error. So they're not a perfect representation of the true latent variable. If we were to repeat measurement over and over again, we'd get a slightly different score. And so SEM is a way of getting, perhaps, at those true relationships, which tend to be, the idea is that observed variables, because there's some unreliability of measurement, that's an error, and that reduces the relationships we observe. Another nice thing about structural equation modelling is that it allows for more explicit tests of competing models of relationships between variables. So you can formalize quite explicit models of how a test works or how different variables relate. So for example, in my research at the moment, looking at the structure of Big Five personality, there's questions about whether the factors are correlated, whether there's a higher order factor above the Big Five, whether there are maybe multiple. There's a theory of the Big Two that says, I think, that extroversion and openness kind of hang together as a general self-actualization factor, and neuroticism, conscientiousness, agreeableness sort of hang together as a general socialization factor. So these kind of models. There's models that say that, there's certain items that cross-load or capture different method variances. There's all these different kind of representations of, say, a test. And SEM provides a framework for testing competing models and saying which one is a better representation of the data. So yeah, specific kind of applications which you might come across in org psych. One of the biggest is scale development. If you're developing a scale for your thesis, or you're in a job where you're refining a test, this is a really great tool. You might start with exploratory, then transition to confirmatory, and so on. And you can also refine things a lot, and it's pretty standard these days. You'd be expected to report confirmatory factor analysis if you're developing a new test. Mediation and complex pathways, longitudinal stuff, that's big. You can also do between group comparisons. So measurement equivalence, you might hear about. Has anyone heard of that concept? So people who are doing cross-cultural research often want to know whether a test is behaving the same in two cultures. If you're interested in diversity issues, you might be looking at, does this test behave the same in males and females, in whatever the dominant group is in the culture versus some minority group? These are the kind of group comparisons that you can test in SEM. So what is SEM, or structural equation modeling, in a nutshell? There's a few ways of thinking about it. One is, it's a graphical representation of the pattern of relationships between variables. That's sort of a very kind of high-level idea. In another way, it's kind of like a mixture of factor analysis and multiple regression, or dare I say, a set of multiple regressions. You attempt to build a model that captures the correlations between your variables, or the covariances between your variables. Sometimes people actually call it covariance modeling, because there's a set of relationships between your variables. Each item correlates with every other item to a certain amount, and you're trying to build up a model that captures those covariances. In fact, even the name Amos stands for analysis of moment structures. And has anyone ever thought what a moment is? They probably say, well, I was with my partner the other night and we had a moment. But in statistics, moments are properties of variables. So the first moment is the mean, the second moment is the variance, and the covariances are, in a sense, a moment. So it's an analysis of the structure of moments, which are means, variances, covariances. So that's what we're modeling. We're modeling the relationships between variables and trying to produce a model that is parsimonious, theoretically justifiable, and represents the observed correlations and covariances. So parsimonious means you don't have more relationships than are necessary. There's a general sense that SEM builds on all your knowledge of this sort of basic stuff. Well, who knows if it's basic or not, but it is what it is. So it builds on an understanding of correlation and covariance. So by correlation, we're talking about the linear relationship between two variables, and we generally characterize a correlation in terms of its form, and generally we're talking about linear relationships, so more of one variable, more of another. The direction refers to whether it's a positive or negative relationship, and the degree refers to the strength of that relationship. Do we have a strong 0.6, 0.7 correlation, or a smaller 0.2, 0.1 correlation? Covariance is just unstandardized correlation. So it's just on the metric of the raw variables. So it describes the degree of relationship between the two variables of interest on the raw metric. We've gone through exploratory factor analysis last week, and we definitely draw on ideas from that when we characterize latent variables and when we model latent variables. Reliability feeds in the sense that there are manual ways of correcting for reliability to get estimates of relationships between the underlying latent variables. SEM does that almost automatically. When you look at correlations between latent variables, it's automatically correcting for unreliability or reliability. It also draws on all the ideas of multiple regression in terms of regression coefficients, variance explained, you'll get confidence intervals on coefficients, and a lot of the standard assumptions around, kind of assuming normality, but maybe doesn't matter too much if it's a little bit violated. Outliers can still do all the same things, and so on. Another big thing that SEM tries to do, or the language of it tries to do, is causal inference. So a lot of the time it will represent relationships as directed, which implies that you're making a theoretical claim that X is causing Y. That the latent factor is causing the responses to the observed items, or that time 1 emotion regulation influences time 2 outcomes. It's not always true, and you can always fit a model that implies a causal model. It's not true, but certainly the logic of causal influence is there. We can also distinguish between a few different types of models. Path analysis is where we have an outcome variable or more than one outcome variable, but we have no latent variables. So we've just got observed variables that you put in your model. So these might be you put in your observed total score for job satisfaction, your observed score for personality. In general, path analysis is perhaps not as not as interesting in the sense that one of the main benefits is that you're representing latent variables. But you can do that. You might do it if you had small sample sizes, or you just wanted to stay, you didn't have many items per factor or something like that. Confirmatory factor analysis is what we're going to do today. So this generally means that you've got latent variables explaining items, but you're not looking at the relationships between the latent variables. So you're not saying this latent variable is causing this other latent variable. Once you start having latent variables as outcomes, so maybe you had personality as latent variables and you had job performance with latent variables, and you start predicting job performance, latent job performance from latent personality, then you've got structural equation modeling. You've got a latent outcome variable that is in the model, and that's when you've got SEM. But in many senses, these are just distinctions that we can make in terminology. I've touched on this point here about the exploratory to confirmatory continuum. At the confirmatory end, you've got some either one or more very explicit models, and you're testing them and maybe comparing them. Alternatively, you can be very data-driven in Amos. You can look at these things called modification indices and see what it suggests makes the model better. You can try a whole pile of different models and experiment and so on. So there is this continuum within what they call confirmatory factor analysis, from very data-driven exploratory to a very confirmatory approach. In terms of software, there's a lot of structural equation modeling software out there. State has also got, I've not listed there. I've got experience mostly with SPSS Amos. That's what I was taught many moons ago originally, and I think it's a very nice tool to learn structural equation modeling the first time. I think the Amos was, I think, maybe the first to have a graphical user interface. Others have caught up with that idea. And I think it's quite intuitive about what everything means with the circles and arrows and boxes and so on. That's not to say it's the best. It's certainly, in terms of features, it's missing some features, particularly I think around modeling categorical and really modeling Likert scales in a very formalized way. It has a few features, but I don't know if it's quite as advanced as, say, something like M+, which is, I think most people consider probably one of the best these days for really flexible options. And so yeah, there are courses on M+ that are run around the place. I know Mike Ziffer at Melbourne Uni runs a 5-day one every year, so if you're ever wanting to really dive into M+ for your thesis or your work, then that's not a bad option. Given that I know R and quite like R, I've used the SEM a few times, but now if I have to fall back on one, I use the Levan package. It's kind of modeled in a mental model very similar to Amos. You have to write scripts, of course, but I find them quite intuitive. And in fact, models can get quite complex with all the little residuals and things, and it can actually be quite even simpler and quicker once you learn the syntax to use something like Levan. But yeah, there's options out there. Is everyone just use Amos? Is that their prior experience of those who do? Or yeah. Okay, so let's talk about let's build up a vocabulary of terminology for structural equation modeling. You have rectangular or square boxes, and these are used to represent observed variables. So these are things like the items on your personality test, responses to survey items about job performance, indicators, observed indicators of behavior. Then we have a latent variable. I guess they're curved. And specifically, when we think about it as a latent factor, we would do it as an ellipses. If it's just the residual of an observed variable, like you say what's not captured in an item or in a factor by other things, we would use a circle. So this is a bit like when you do a regression and you're not explaining everything, the thing that's left over is represented by this error variance, which is a circle. These ellipses would be used to represent factors of interest. So a latent intelligence factor, a latent job performance factor, a latent extroversion factor. So there are little things to represent both observed and latent variables. We then start defining relationships between these elements. So if we say that one variable predicts, or in some senses causes, another variable, we would draw a directed arrow. So we generally say that latent variables cause the item, and if we say that, then we would draw a directed arrow between the latent factor and the item. If we're saying that there's a correlation between two variables, we'd do a double-headed arrow. So if you thought extroversion and neuroticism were correlated, you could draw a double-headed arrow between these. So here's some very basic examples, of common situations. You've got two observed variables. I don't know. I'm doing a study at the moment on income and life satisfaction. Income, life satisfaction. So I couldn't be bothered doing latent variable modeling. I could put these two variables in and I'd say there's a correlation. I think it's in the current data set it's about 0.2 cross-sectionally. And so, hey, we run that, we get Pearson's correlation up there. Of course, we wouldn't do that because we could just go to SPSS and get Pearson's correlation by correlating the two variables, but that's the same thing. Or we could run a regression and say, oh, income predicts life satisfaction, so we could draw a directed arrow. And because this is a regression, we're not going to predict all of life satisfaction from income, so we would have a residual variance. That's the variance in the DV that's not explained by the predictor or predictors. Okay, over here on the left, we've got effectively a correlation matrix. We've got 4 variables. I don't know. Could be extroversion, neuroticism, agreeableness, and conscientiousness or something. And you just want to find out the correlation between these 4 observed variables. Could go to SPSS and run a correlation matrix. That's what you probably do. But alternatively, you can put these double-headed arrows and you will get the estimates for all these correlations. Up here, we have a multiple regression. So we've got 3 predictors and 1 outcome variable. So we've got 3 regression coefficients with the directed arrows, and implicitly in the regression model is to say that these variables could be correlated. So yeah, I guess we're showing that we can replicate standard things in SEM. You know, we can replicate correlations and regressions. This top one here is a very standard partial mediation model where we have an IV on the far left, a mediator in the middle, and a dependent variable. So the IV is predicts the mediator, both the IV and the mediator predict the DV. Anything predicted has a residual variance, and we would get regression coefficients for all these pathways. We could also look at the indirect effect as the sort of this times this, so the sum of the 2 parts. We could also look at a fully mediated model by removing this direct effect. And in theory, you could actually test, you know, whether that damaged the fit of your model, whether you're less able to represent the relationship between these variables after taking out this path. Yeah, do people have any questions at this point? All right. Okay, now here's where we're kind of really getting into actual stuff, real latent variables. This little nugget of a structure on the top left here is the classic thing you see when you're representing latent variables. So what we have here, we have 3 little circles, 3 rectangular boxes, and an ellipsis. You could think of this as your personality, or one factor of a personality test that had 3 items. So these are the boxes, the observed variables, a latent factor, so extroversion, say, and you've got items, life of the party, love talking to people, I'm a social recluse, negative item. And yeah, you've got these 3 regression coefficients that are coming from the latent factor. So the idea is the latent factor of extroversion is causing these items to some extent. And each item is not perfectly explained by the latent factor, so you have a residual variance.
Can you have a negative loading?
Yes. So probably there's a couple of points that are worth mentioning in relation to reversed items. But yes, you can certainly have a positive or a negative item, and that would then, this will be like factor loadings in here.
Yeah.
You'll get a positive, positive, negative, whatever. Okay, so what's this little 1 here on this directed arrow? That's the one thing that you might want to think about. In order to give this latent factor a scale. Does that make sense? So you've got this latent variable. What metric is it on? You know, is it a z-score kind of variable, or is it on some other metric? So you have to give it a metric somehow so that it has meaning and has a scale so that the regression coefficients make sense. So the 2 ways of typically doing that is either to constrain one of these loadings to 1, and that sort of just cascades out to give this a metric, and then the others are sort of based on the size of this loading. Or you can constrain the variance of the latent factor to, you know, have a variance of 1, for example. And then this becomes a z-score. And therefore all the loadings are kind of on a z-score kind of metric. So for a 1 standard deviation increase on this, what's the effect? Just without wanting to get too off track, the key thing to do is, if the default is to have a 1 on one of these loadings, key thing to remember, and this will be important for the assignment because this occurs and it is an issue, always make sure that the 1, if you're constraining an item, is on a positively worded item. Does that make sense? So in my previous example, I said, oh, social recluse is this 3rd item. So if you've got the 1 on that negatively worded item, this is no longer extroversion, it will be introversion. So the direction of the factor is governed by the direction of the item that receives the 1. So, yeah, if you have scales, like you're doing the assignment with positively and negatively worded items, make sure that the 1 constraint is on a positively worded item. Otherwise, well, you just have the opposite of what you think you have. But we'll go through some examples of all this in a bit. On the right here, we have what's more commonly seen in the confirmatory factor analytic settings, where you've got multiple factors. So this could be what's a you want to think of a 3-factor model of something. This could be theory of planned behaviour, and you've got attitudes, subjective norms, and perceived behavioural control. And for each of these domains, you've got 3 observed items. And so we've got this far left structure, but applied for each factor. So we're estimating these latent variables. And then in turn, we can estimate the correlations between the latent variables. So here's something that we haven't actually done, we couldn't do easily with SPSS. You can correlate observed extroversion scores with observed neuroticism scores, but it's another level to correct for reliability and estimate the relationships between these latent variables. So that's confirmatory factor analysis on the right. And where it becomes structural equation modelling is when we start saying, oh, one of these latent factors is an outcome variable. So this top right here looks very similar to this. We've still got 1, 2, 3 latent variables, each with 3 observed items and residuals. But we've decided, oh, actually one of these is kind of an outcome that we're trying to predict. So now we've got directed arrows coming into an outcome variable. So this could be a couple of personality variables, and this is a job performance factor, each with indicators. There's nothing special about 3, well, there's something a little bit special, but you can certainly have 4, 5, 6, 7, 8 indicators. 3 is often necessary for identification of your latent variable. If you only have 2 indicators, then you often have to do other things like constrain both loadings to be equal and a few things. But yeah. So this is what Amos looks like. This is just a simple example with a couple of latent variables. This was perceptual speed ability, psychomotor ability. Each measure had 3 tests, like a sorting numbers, comparing numbers, and simple reaction time, 2 choice, 4 choice for a psychomotor ability. And there was task performance, which was an observed variable, so we correlated that. We'll go through this interface a whole lot more in an example, I think. But in general, Amos allows you to draw observed variables, latent factors, as well as there's a dedicated tool to create these little confirmatory factor analytic nuggets, if that's a word. So latent variable indicators, residuals. When you're doing regressions, you'll need to add specific residuals. You can also do directed arrows, correlation. And it's kind of a bit like old school Qt. When it comes to moving objects, there's a truck. If you want to copy objects, there's a photocopier object, and you press that. Yeah. You get used to it, and I think part of the skill of Amos is just learning the tricks to draw diagrams quickly and efficiently. Once you set up your model, you can configure the options. I sometimes wonder, the save dialog box, like when people see a floppy disk, are they actually going to know what that is in a few years, or even maybe it's hit already, I'm not sure. This is even more old school. I think this is an abacus. So if you want to run the model, you click the abacus, I guess. And the top one with the abacus is the options for the running. You can also toggle between modifying the model with this left down thing versus viewing the output on the right. Yeah, lots of the tricks are really around how to do this quickly and effectively. All right, so what do we actually do with all this stuff? In terms of testing some models and building up some arguments and some findings, you've got to think about what your models are and what kind of models you want to test and whether you're going to be confirmatory or exploratory in your approach. Once you've sort of sorted out all your basics of your data, you may run exploratory factor analysis first, just to get a feel for it, or if you're being a bit more top-down, you might jump straight into confirmatory. But yeah, you've got to estimate the model, so estimate the parameters and the fit of the model, and interpret what the coefficients mean, as well as what whether the fit is good relative to other models and in general relative to criteria that are out there. You may then modify the model, add some terms, add some covariances, remove variables, and so iterate and get to a better model. So what are parameters that you might be interpreting in such a model? Well, we've seen you can get correlations and covariances. So how do two latent factors correlate? How do the big five correlate, for example? You also get unstandardized and standardized weights. So a weight really is just like what we see in a regression coefficient or factor loadings in a factor and analytic context. So standardized is like a standardized beta or what we see in a pattern matrix. So for a 1 standard deviation increase on X, what's the standard deviation increase we see on Y? And we also get unstandardized versions. Commonly in psychology, we're not as interested in the scale of things because the metrics are a bit strange, but yeah, so we'll often focus more on the standardized output. We also get variance explained in many contexts, which is basically like R squared in a multiple regression. So variance explained in an item or variance explained in a dependent variable in some sort of regression type model. Yeah. When we assess fit, there are a whole range of indices to describe how well our model represents the covariances between the items. A lot of them are in one way or another based on the chi-square, where larger chi-square means poorer fit. So many of the other measures make corrections for the number of parameters you're estimating, so penalize more complex models. And a lot of people will quote things like Hu and Bentler for rules of thumb. So these are just some rough guides, and Hu and Bentler is sort of the classic reference that everyone plonks into their journal articles and their thesis as a basic frame of reference. Although these rules of thumb can vary quite a bit based on what kind of model you're fitting. So when you have a lot of observed items and not so many factors, you're generally going to get worse fit, and that in some ways is okay. An alternative approach rather is to fit multiple models and actually see which model is better or worse rather than relate them to global rules of thumb. The SRMR looks at how much the observed covariances differ from the modeled covariances, and CFR looks at the kind of proportion of deviance that's sort of recovered by the model relative to a null model. But yeah, there's lots of measures of fit, and if you get into it, then you might want to read up about them in a book like Hare et al. Or Tabachnik and Fidel. So yeah, the general reporting strategy is to report a selection of fit measures, and I think the ones I mentioned above are a good starting point. And if you're looking for a default for your assignment, that's probably a good strategy. But there's lots of discussion about what each of them picks up and so on. So I talked about the idea of fitting multiple models, and what I guess there's a question about what that even means in the context of a personality test, for example. It's often nice to fit a really bad model that's ultra simple, so that it's a frame of reference for how well your better models are improving the situation. So for example, a really simplistic model of the Big Five would be a single factor and everything loading on that. It's not a great model because surely there are discrete pockets of variance, but it's a starting point, and it can also tell you how good alternative models are. You can look at the question about whether latent factors are correlated. You can look at whether there's a higher order factor model that might be explaining relationships between factors. And you can also tweak things by adding cross-loadings. Like when you see an exploratory factor analysis where an item loads on more than one factor, you can add those additional pathways. Or you could say, oh, two items share a lot in common. They're almost identically worded items. I'll allow their residuals to correlate, and that might capture some of the features in the data. So by comparing these different models, you can gradually refine a better representation of a test, and perhaps more generally, the constructs of interest. You can modify models based on theory, but there are these things called modification indices, which can suggest changes you can make to your model which would improve your fit. This is quite data-driven in a sense. So it can suggest a cross-loading that might improve your model. So maybe you've got an item that has elements of conscientiousness and extroversion. So maybe it makes sense to add that cross-loading, so the item loads on both factors. The idea is to choose modifications that both improve the fit, but hopefully they make some theoretical sense and you can sort of justify them. There is an element of you don't want to pick too much up on the noise in the data. So you like to think that what you're adding makes theoretical sense.